In this video, I'd like to talk about the idea of writing a number using scientific notation. And scientific notation is essentially a way to write a really big number or a really small number in a nice compact form. For instance, if you take this number here, 432 billion, we can use scientific notation to write it in a much smaller form, so that essentially we don't have to write all these zeros. And the way to essentially do this is to essentially count how many times you'd move the decimal from where it is now so that it's between this first number and the second number. So it's always going to be one number followed by a decimal and then whatever remaining numbers you have. So in this case, 3, 2, and we won't write all these zeros. The way that we account for all of that is we multiply this by 10 to some power. And that power will be how many times did we actually move the decimal. Since multiplying by 10 would move the decimal once there, then by 100, 1,000, 10,000, and so on. So we just need to count. It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we moved it 11 times. So we would rewrite this as times 10 to the 11th power. And the way to think about this, remember 10 to the 11th or 10 to really any power, let's say to the 6th, is just a 1 followed by 6 zeros. So 10 to the 6th would be 1 million. So 10 to the 11th would be 100 billion. So essentially you can see that we're just taking 4.32 and multiplying it by 100 billion. So that's why we have 432 billion. And like I said, scientific notation is just a great way to write really big numbers in essentially a smaller form. Like if you look at the number a Google, so 1 Google is a 1 followed by 100 zeros. And it's essentially just inconvenient to write out 100 zeros. So we needed, or I should say scientists needed a way to write this so that it's just much more compact and easier to write. And with scientific notation, this would just be 10 raised to the 100th power. And essentially 10 to any power is a 1 followed by that many zeros. One other nice useful way to use scientific notation is if we want to know how many atoms are in the body. Now that would usually be a 1 followed by maybe about 26 or 27 zeros, but it's just much easier to write it as 10 to the 26th or 10 to the 27th power, so it's probably somewhere in between those. And I mentioned that scientific notation is also very useful for writing tiny numbers. So if you had something like 0.00, let's say there are 30 zeros here, and then a 1, this would be 1 times 10 to the minus 30 power. In this case, you're essentially dividing by 10 30 different times. So a number, let's say we had 0.0035, you would still write scientific notation essentially the same way, where we want to put our decimal between the first number and the second number. So you had 3.5 times 10 to some power, and we have to count how many times we move the decimal. And since this number is smaller than 1, we are essentially dividing by 10 multiple times, and so that's why we're going to have a negative decimal, or a negative exponent here. And we moved it 3 times to the right, so it would be times 10 to the minus 3. Or in other words, we essentially have 3.5 divided by 1,000, or 3.5 thousandths. So let's go through a few different example problems. Let's say for our first example that we have 258 million, and we need to convert this to scientific notation. So we know we want to put the decimal between the first and the second number. So we have 2.58, and we don't want to write all these zeros since the scientific notation will essentially take care of that. And we'll multiply this by 10 to some power. And since this number is bigger than 1, it's going to be a positive exponent here. So we just got to think, how many times do we move the decimal? So 1, 2, 3, 4, 5, 6, 7, 8 times. So this would be 2.58 times 10 to the 8th power. And looking at a second example, let's say we have 0.0000287. And again, we want to put the decimal between the first and second numbers, not including all these zeros. Now, if there was a zero between here, that would count. But if the zeros are before or after the numbers, then we don't count those. So this would be 2.87 times 10 to some power. And since this number is less than 1, our exponent's going to be negative. So we just got to count how many times we move the decimal. So we got 1, 2, 3, 4, 5, 6, 7. So we move it 7 times. So this would be times 10 to the minus 7 power. And we can ask a further example problem here. Let's say we want to know what 11 10,000ths would be in scientific notation. And to begin, we got to put this as a decimal. So first, let's mark out at least enough places to the 10,000ths place. So this is the tenths, hundredths, thousandths. So this would be the 10,000ths. And so we would have 11 of those. So we can fill in the 2 zeros there. And we could rewrite this. We want the decimal between the first and second numbers. So we want 1.1 times 10 to some power. And because we're less than 1, this is going to be a negative exponent. We're essentially dividing by 10 a few different times. And we can count 1, 2, 3 places. So this would be 1.1 times 10 to the minus 3 power. And let's do one more problem that's similar to this third example, but a number bigger than 1. Let's say we have 312,000, and we need to convert this to scientific notation. So first, we need to write this number out in its decimal form. So we have 312, and that's all in the thousands place, and then we have our hundreds, tens, and ones places. So this is 312,000. And we want to put the decimal between the first and the second numbers, so we get 3.12. We don't need to include all these zeros. Now, if say this was a 1 here, then you would have to put 0, 1. But since they're all zeros after the last number, we don't have to include those, and the scientific notation will essentially take care of that. And at this point, we just count 1, 2, 3, 4, 5 places that we move the decimal. And since this number is bigger than 1, it will be a positive 5.